All right, welcome. Let's talk about statistics. And I know what you might be thinking, formulas, dry textbooks, but forget all that for a minute. We're going to look at statistics as what it really is, an incredibly powerful toolkit for making sense of our messy, complicated, data-filled world. So to get us started, let's picture something kind of weird. Imagine you're a marine biologist and you're looking at a bunch of oysters. You start counting these tiny little jellyfish polyps that live on their shells, and what you find is the numbers are all over the place. One oyster has 85, another has 220. So right away, you're going to ask a question, right? Why the huge difference? Is it just random luck, or is there something else going on? You know, maybe bigger oysters have more surface area, so they can host more jellyfish. That question, right there, is the starting point for a statistical investigation. You see, to get from just a pile of numbers, like our jellyfish counts, to a real, solid answer, you need a method. I want you to think of it like a detective showing up at a crime scene. They don't just stand there and stare at the clues. No way! They have a specific toolkit, a process for collecting, analyzing, and connecting the dots. For us, that toolkit is statistics.
Okay, let's do it. Let's open up that toolkit. For the next little while, we're all going to be data detectives. And these first few tools are all about understanding the most basic clues you can find in any set of data.
So, what's the very first job of any good detective? You gotta describe the scene. Before you can even think about finding patterns or jumping to conclusions, you have to get a really clear, honest picture of the evidence right in front of you. Okay, check out these two sets of numbers. Just at a quick glance, both of them, dataset X and dataset Y, they seem to be hanging out around the same value, don't they? Kind of centered around 20. But hold on. If they're both centered around 20, does that mean they're telling the same story? Not at all. Look a little closer at set Y. Those numbers are way more spread out, right? They go all the way from 9 up to 28. Set X, on the other hand, is packed in really tight. That difference is absolutely critical. So to really nail down that center, we've got a couple of tools. First up is the mean. That's just the average you learned in school. Add them all up, divide by how many there are. But we also have the median. That's the number that's physically in the middle once you line all your data up. And here's the key. The median doesn't really care about one or two crazy high or low numbers. It's more stable.
But here's the thing. Knowing the center is only half the story. You have to measure the spread, or what statisticians call dispersion. This tells you if your data is all clustered together, like our set X, or if it's all over the map. And we have tools, like variance and the interquartile range, that put a hard number on just how spread out things are.
And you know what? There's an amazing way to see that whole story, center and spread, all in one picture. It's called a boxplot. It was invented by a genius statistician named John Tukey. That box in the middle literally shows you where the middle 50% of all your data is hiding. It's such a brilliant at-a-glance summary of everything. Okay, so up to now, we've been looking at one thing at a time. But this is where the real detective work kicks in, when you start looking for connections between the clues. Like, is there a link between how big an oyster is and how many jellyfish it has? That's what this next set of tools is all about. And our go-to tool for this is the scatter plot. Think of it like spreading all your evidence photos out on a big table. Each little dot is one observation, in this case, one iris flower, and it's plotted based on two of its features. Just by looking at the shape of that cloud of dots, you can immediately start to see if there's a pattern. Now, we can actually put a number on what we're seeing. Covariance is a measure that tells us the direction of the relationship, like do these two things tend to go up together? But correlation is the real powerhouse. It gives you a single number from -1 to +1 that tells you the direction and the strength. A correlation close to 1 or -1 means you found a really strong connection. And if we see a trend, we usually want to draw a line through it, right? To summarize it. That's exactly what linear regression does. It's a method that finds the one single straight line that best slices through that cloud of data points. It's the detective's best summary of the underlying trend. Okay, deep breath. This is a huge moment in our journey. Everything we've done so far has just been about describing the clues we have right in our hands. Now, we're about to make the great leap from our small handful of clues to the entire world. This is the heart and soul of what's called statistical inference. I mean, think about it, right? We can't measure every single oyster in the ocean. We can't poll every single voter. In the real world, we are always working with a small sample. So the million-dollar question is,
How do we use that tiny little sample to make a smart, reliable guess about the whole population?
So let's try a little thought experiment. What if we took a sample of, say, 30 oysters and calculated their average polyp count? Okay, now what if we did that again with a different 30, and again, thousands and thousands of times? What would the graph of all those thousands of averages look like?
And here is where the magic happens. It's almost unbelievable. Even if the original data for individual oysters was lumpy and weird, the distribution of all those sample averages will form a perfect, beautiful, normal bell curve. This incredible result is called the central limit theorem, and it's basically the foundation of all modern statistics. It's a huge deal. So, because we know this predictable bell curve pattern exists, we can use our one sample to work backwards. We can calculate a range of values and then make a statement like, okay, based on my sample, I am 95% confident that the true average for all the oysters in the entire ocean is somewhere in this range. That range is what we call a confidence interval. All right, now that we have these powerful tools, we can do something really cool. We can formally test a specific idea or a claim. This is where the data detective goes from just gathering clues to actually standing up in a courtroom and building a case.
You can think of every statistical test as a showdown. It's a fight between two competing ideas. On one side, you have the null hypothesis. That's the boring, default idea that nothing is going on. No effect, no difference. And on the other side, you have the alternative hypothesis. That's the researcher's hunch, the exciting idea they're hoping to prove.
Yeah, just think of the null hypothesis as the big skeptic in the room. It's the voice saying, nope, sorry, nothing interesting is happening here. That pattern you think you see, it's just random luck. And our job as the detective is to see if we can find enough evidence to prove that skeptic wrong. So you've got your two competing stories, the skeptic versus the researcher. How do you decide which one is more believable? Well, it all comes down to one single, super important number. In a real study looking at a cholesterol therapy, after all the data was collected and all the math was done, this number popped out of the computer. This is the famous, and let's be honest, often misunderstood, p-value.
And this, right here, is the million-dollar question. Is that number, 0.06281, is it small enough for us to reject the skeptic who says the therapy does nothing? What does this number even mean?
Okay, here's the key to understanding this. The p-value is the chance of seeing the data we saw if the skeptic was right all along and the therapy actually had no effect. So if that number is really, really small, it means our result would be a massive surprise if nothing was going on. And if it's surprising enough, usually if the p-value is less than 0.05, we say, you know what, I'm rejecting the skeptic's view. So in the end, even with a really small p-value, we haven't proven anything with 100% certainty. And that's okay. What we've done is use this incredible framework to weigh the evidence and make a smart decision when we can't be sure. Statistics doesn't give us absolute truth. What it gives us is a disciplined, powerful way to manage and quantify our data.